Hey everyone, I am absolutely thrilled you're here. Today we're exploring something that basically runs your entire modern life, but you can't even see it. Literally right now, as you're sitting there, you are swimming in this invisible, pulsing ocean of waves.
Okay, let's dive into this. What do a sunburn from a day at the beach, a quick text message to a friend, and a hot microwave dinner possibly have in common? I mean, on the surface, they seem totally unrelated, right? But fundamentally, they are the exact same physical phenomenon, just packaged in different sizes. We're talking about the electromagnetic spectrum.
To make sense of this massive topic, here's our game plan. First, the invisible ocean. Second, wavelength, frequency, and energy. Third, engineering the right wave. And finally, radiation, safe versus ionizing. Let's get right into it.
Part 1. The Invisible Ocean. Understanding Electromagnetic Waves.
Now, what's really interesting about this is that an electromagnetic wave isn't a physical object you can just grab and hold. It's actually made up of two distinct fields, an electric field and a magnetic field, and they're oriented at perfect right angles to each other. Together, they create this moving disturbance that actually carries energy through space. To truly appreciate this, we kind of have to contrast it with something we're all very familiar with, which is sound. Sound is what we call a longitudinal wave. It actually needs a medium, like air or water molecules bumping into each other, kind of like a line of falling dominoes. But electromagnetic waves, they're transverse waves. The displacement is perpendicular to where the wave is going, and miraculously, they don't need any molecules to travel at all, which means they can move completely unhindered through the dead, empty vacuum of outer space. Pretty wild, right?
Moving on to Part 2. Wavelength, frequency, and energy. The physics of the spectrum.
300,000 kilometers per second. That is the speed of light in a vacuum. It is literally the absolute universal speed limit. Whether we're talking about a radio wave or a gamma ray, every single wave on the electromagnetic spectrum travels at this exact same speed. So, because that speed is constant, the differences between all these types of waves really just come down to their physical size and how fast they cycle.
I like to call this the seesaw effect. Imagine a giant seesaw where one side is wavelength, so the physical distance between two wave crests, and the other side is frequency, how many of those waves pass a certain point in 1 second. As the physical wavelength gets shorter, meaning it goes down on our seesaw, the frequency goes up. And here is the absolute golden rule of physics you need to remember. The energy of a wave increases with its frequency, so short, extremely fast waves pack a massive energetic punch. Think about radio waves for a second. They have low frequency, they have low energy, and their physical wavelengths can literally be the size of entire buildings. Now, right in the middle, we have visible light, which is tiny, measured in nanometers. But compare that to the other extreme, gamma rays. These guys have incredibly high frequency, massive amounts of energy, and their wavelengths are actually smaller than the nucleus of an atom. No way, right? It's mind-blowing.
Part 3. Engineering the right wave. Harnessing the spectrum.
So the crucial point here is that engineers don't just pick these waves at random. When they're designing a new piece of technology, they have to carefully calculate some very specific trade-offs. They've got to consider propagation distance, how far can the wave travel before it loses power? They have to consider data transfer speed. And critically, they have to account for atmospheric absorption and whether the wave can actually penetrate physical objects like walls or even human tissue.
Let's look at those practical trade-offs. Lower frequency waves, like radio and microwaves, well, they're fantastic for long-distance communication. Their massive, long wavelengths allow them to easily pass through the atmosphere, foliage, and most building materials. Higher frequency waves, on the other hand, like visible and ultraviolet light, they're easily blocked by surfaces. But their rapid frequency makes them absolutely incredible for packing in high-speed data, which is exactly how fiber optic internet cables work. Let's look at a really specific real-world example. Microwaves. Engineers specifically select microwaves for weather satellites because this unique frequency band can easily penetrate the Earth's atmosphere, but it also interacts brilliantly with water molecules. So, it allows us to map weather patterns from space. And down on the ground, that exact same interaction with matter is why your microwave oven heats up the water inside your food. So yeah, you can literally thank the electromagnetic spectrum for both tracking global hurricanes and heating up your leftover pizza. Oh, and a slightly different microwave frequency? That's what your home Wi-Fi router uses to send data right through your living room walls. And this brilliantly illustrates just how surrounded we are by this stuff. From the GPS tracking your car using radio waves, to night vision goggles relying on infrared, to the optical communication of visible light, right up to the X-rays imaging our bones, almost every single modern convenience is really just a meticulously engineered flavor of the exact same electromagnetic phenomenon.
Which brings us to part 4. Radiation, safe versus ionizing.
To really understand radiation risks without all the anxiety, we have to understand one key term: ionizing radiation. Remember our seesaw? Well, only waves on the extreme high-frequency, high-energy end of the spectrum possess enough raw power to actually knock an electron right off an atom. When an atom loses an electron, it's left in a state of electrical imbalance. It becomes what we call an ion.
So here is the firm scientific line we really need to draw. Non-ionizing radiation, like the radio waves from your cell phone or the visible light from your desk lamp, has low energy. It might vibrate molecules and create a little bit of heat, sure, but it absolutely cannot strip electrons. It's considered safe. Ionizing radiation, however, stuff like ultraviolet, X-rays, and gamma rays, has high energy. It can strip electrons, it can cause chemical reactions, and it can literally alter the DNA molecules within living cells.
But where do we actually encounter this high-energy ionizing radiation in everyday life? Well, according to the CDC, it comes from both natural and man-made sources. Naturally, we're exposed to cosmic radiation from space, and, even more pressingly, radon gas. That's a naturally occurring radioactive gas found in rock foundations that can actually leak into homes. On the man-made side, our primary exposure isn't nuclear power, though yes, that is a source. Our main exposure actually comes from diagnostic medical exams, things like X-rays and CT scans.
The CDC puts the risk very clearly, stating that ionizing activity can alter molecules within the cells of our body. That action may cause eventual harm, such as cancer, because intense exposures can produce visible tissue damage, like a really severe UV sunburn, and over time, that cellular damage can lead to serious issues. In fact, radon gas exposure is the second leading cause of lung cancer in the United States, so great safety precautions are absolutely crucial when dealing with these high-frequency waves.
Let's move to and see how this builds into our daily lives. How can we use this knowledge to empower ourselves? Because diagnostic medical imaging is our main man-made source of ionizing radiation, the CDC highly recommends tracking your imaging history. The goal is always for the diagnostic benefits to far outweigh the radiation risks. And by understanding this spectrum, you can have much more informed conversations with your doctor. You might even ask if a zero-ionizing radiation alternative, like an MRI or an ultrasound, could provide the exact same diagnostic benefit without any of the cellular risk.
So, from building-sized radio waves carrying our voices across the globe to microscopic gamma rays holding the power to alter our very DNA, we truly are living in an invisible ocean of energy. We've mastered it to the point where our modern society simply wouldn't function without it. But it leaves me with one final, totally fascinating thought for you all to ponder. Since every single text message, weather satellite, and medical scan relies on this incredible invisible ocean, what part of the spectrum are we going to engineer next? Thanks for joining me on this explainer, and keep learning.